One of the other things we can do is use this concept to help us solve out certain scenarios. So in this case, I'm going to take a matrix B that's going to be a function of lambda, if you will. So here's our matrix, and what we want to do is we want to find lambda so that B is singular. And we could really ask that question either way. We could ask that B is singular, we could ask that B is non-singular. In this case, this is just what we're doing. So remember, for it to be singular, we have to make sure that the determinant is equal to 0. So we compute the determinant of our matrix, which is just 4 minus lambda squared. And for the matrix to be singular, we have to have that the determinant is equal to 0. So we set it equal to 0. And now we have a quadratic equation that we get to solve, which is not terribly complex. We can see pretty quickly here that that implies that lambda is plus or minus 2. So these are the two values for lambda that will make B a singular matrix. And we can also do that with maybe a 3 by 3 matrix. Here we see a nice 3 by 3 matrix. And again, let's figure out what lambda has to be in order for this matrix to be singular. So we again need the determinant of this particular matrix. And I've already done that computation. So we have that the determinant of B in its simplified form is going to be equal to 2 lambda squared minus 8 lambda plus 6. Again, for our matrix to be singular, we have to have that the determinant is equal to 0. So we set the quadratic equation to 0 for our singular condition and just factor and solve. So in this case, you end up with 2 lambda minus 2 times lambda minus 3 is our factorization, which means there's a couple solutions here. Lambda is going to be equal to 1 or possibly 3. So again, these are the two now values of lambda that make our matrix B a singular matrix.